Hey guys, have you heard of any waste that's being sold in a market? Now, in this session, we are going to discuss about one such waste that is actually sold for a price. Now, according to the norms of our government, central institutions are required to purchase any research component from a specific portal, and this is an e-commerce portal that is maintained or rather monitored by our government, and we are encouraged to purchase our research components and any similar components from this portal. And in this portal, as you can see here, the blast furnace slag is being sold. So blast furnace slag is nothing but a waste that is generated during blast furnace operation, and here you see that it's being sold for a price, so it's being sold profitably. Now, if a byproduct of an operation is being sold for a profit, should we actually refer to it as a waste? So that is one of the questions that pops up. And the second question is, if people are ready to buy this waste for a price, why should we worry about managing them? So we are considering this topic in the context of metallurgical waste management. So blast furnace slag is a seemingly wasteful byproduct of blast furnace operation. So we have to address these two questions on why, if it is sold for a price, we have to treat it as a waste, and secondly, if it is sold, why should we have to consider managing them? Why cannot we just keep on selling it? Now, the answer lies in the amount of such blast furnace waste that we produce. So here you can see both the projection of how much iron and steel we will be consuming in the future, we will be requiring in the future, and also how much we have been consuming in the past. And it is compared with the consumption of aluminium, the second in the line, and its projected consumption. So if you compare these two charts here, and particularly if you focus on the scales, you would see that despite the discovery of several materials, the usage of several materials, the engineering of several materials, you would find that the iron and steel, they rather are one order greater than that of the consumption of the next metal and alloy, that is of aluminium. So it means we are not only producing exceeding amount of iron and subsequently steel, but we are also going to produce them in an exceeding level in the days to come. So consequently, the amount of waste that is going to get generated from these processes are going to increase. So we need to have a ways to manage them. Not all of these wastes can be sold in the market. But still the question remains, why is it sold for a price? And that is what we will rather describe in these series of sessions. So how useful should it have to be for it to be sold for a price? How potential should this blast furnace slag hold for it to be sold in the market? And that is exactly what we are going to discuss in not only in this session but also in the sessions to come. Now, one rather cult-like example that we can talk about or we can give to that of steel is that in one of the discussion, Elon Musk, he talks about why he chooses to use a form of steel, that is stainless steel, in his rockets. So often when we talk about aerospace application, our mind directly goes to lightweight materials. We talk in terms of aluminum alloys, and if you want to have a more engineered form of a material, we talk about composites. But here you can see Elon Musk in this interview discusses as to why he uses stainless steel. So it means that in application which is often associated with lightweight materials, the use of steel is also something that is prevalent, and that is something that we will see in the days to come. And for that reason and similar other reasons, in the last 20 years there have been the 3500 grades of steel that have been developed, and that means that we have identified specific applications wherein these steels can be put to use. So, and that is the reason primarily why, because of these generation of steels, because of these productions of steel and associated productions of its waste, the slag, there are several associations that have been constituted in order to manage these slag that are getting produced along with the manufacturing of steels. So in the days to come and also in the days behind us, we have been using significant amount of steel. We have been generating significant amount of, or we are engineering significant grades of steels. So they have contributed enormously to the amount of slag that has been generated. So in order to manage them efficiently, several associations have been formed. So you have, of course, US Association, Euro Association, and Australian associations, and soon hopefully we will also have an association of our own. Possibly you guys can come up with one. So all these are constituted primarily rather to manage these slag. Just a quick review of how these waste is produced, or this slag is rather produced. So this is primarily a waste that is generated during the extraction of iron. Now iron is available in our surface of the earth in the form of a mineral, and this mineral is nothing but a compound. So if I want to extract iron out of this compound, I have to break this compound down and I have to separate the impurities from that of the iron. Now in order to separate that, in order to reduce, both technically and also in a colloquial way, in order to reduce this mineral, this compound, into that of the iron, I use an agent the form of coke, and this coke ensures that my mineral, which is a compound, gets reduced into iron that is desirable to us. Once this impurity is separated, we want to have this impurity, we want to separate out this impurity from that of the iron that we get at the end of the blast furnace operation. Now for that purpose we use flux. So the coke that we use separates the impurity from that of the iron. Of course I don't want to get into the specifics of it, this is not the appropriate place for it, but just I want to give you an overview of it. So I have my ore of iron in the form of a compound. I want to separate the impurities from that of the iron, so I use coke and I use flux in order to ensure that these separated impurities form a consolidated slag that can be separated out. Now this slag is what? This consolidated impurity that is possible for me to separate out, that is formed through the flux, is what I refer to as the slag. And slag essentially is so-called the waste or not so useful component of my blast furnace operation. Now if I want to make use of this slag, if I want to essentially manage this slag, I need to know its chemical composition, and this representation here gives an amazing overview of the chemical composition of our slag. So just these three corners, let's say, indicate what are the primary components that constitute our slag. So one we have is SiO2, CaO, calcium oxide, silica, calcium oxide, and aluminium oxide. Now the composition, the exact amount of these components that are present in the blast furnace is given here. So Fe, so essentially this bluish thingy here, the bluish region, they indicate the composition of our slag, and as you can see it primarily comprises of silica, calcium oxide, and also aluminium oxide. So these are constitute, so these components, they essentially constitute, depending on the ore from which we extract our iron. The composition may vary, but these are the primary components of our slag. And once, so understanding the chemical composition of the slag is rather the first step to understand or to ascertain how we are going to manage our waste products. So now we have an overview of what is the composition of the slag that we are going to manage. Now, it is often claimed that, or this paper, particularly this particular paper here, it is often cited as a source for stating that the slag that is generated from a blast furnace operation is a non-hazardous waste. So of course there are two reasons why it is referred to as the non-hazardous waste. You have a technically rigorous work reported in this article, based on which we can state that it is often stated that, like here, it is often stated that the slag, the byproduct that comes out of the blast furnace operation, is non-hazardous. And one other reason is, if you consider the clay that surrounds us, that we can find on the surface, that we can find essentially on the surface of the earth, is nothing but alumino-silicate mineral. The clay is in itself is an alumino-silicate mineral, meaning the sand is essentially something similar to the sand that we see, that we walk on, as a composition something similar to that of our slag. So based on these, it is often claimed to certain degree of accuracy, it is claimed that the iron slag is a non-hazardous waste. However, you need to understand that this particular study considers the blast furnace slag that is generated by 50 different blast furnace units, but all these units are associated with, or they are all located in US. So this study, even though it considers 50 different blast furnace slag, exhaustively studies their chemical composition, it still does not consider all the iron plants or iron making plants around the world. It is rather localized to United States. So therefore, it is not always the case that the blast furnace slags are non-hazardous waste. The reason we have to point this out is primarily because had they been a completely non-hazardous waste, we don't have to consider waste to manage them. If they are waste that are non-hazardous, they are not going to in any way harm the environment or us. We don't have to exclusively study their management techniques. All we have to do is just scatter them around the surface of the earth. But unfortunately, these wastes, or only some of these wastes that are generated in some of these plants because of their nature of the mineral that they are handling with, they are non-hazardous. And there are hazardous forms of slags that get generated during the blast furnace operation. The hazardous nature of these blast furnace slag essentially comes out of the possibility of heavy metal ions getting leached out of these slags. So essentially what we mean by that is, if I take this understanding of our slag being non-hazardous in nature, and if I keep on scattering it on the surface of the earth, it is possible that during some season, the heavy metal ions, when exposed to the atmospheric condition, these heavy metal ions can get leached from these slag and they get mixed up with my water body and ultimately contaminating the water that surrounds us. So this is something that we need to avoid. This is something we need to somehow prevent, and this can only be prevented if we properly manage our blast furnace slag. And for this reason alone, we cannot categorize the entire blast furnace slag as a non-hazardous waste. We have to look for the possibility of leaching these heavy metal ions. As you can see, some of these heavy metal ions are harmful to us and also harmful to the environment that surrounds us, the plant and the animal ecosystem that surrounds us. So some of these elements might be rather not so harmful in trace levels, but if the amount of these elements increases, they are going to be ultimately harmful to us. So before we decide on how to manage the blast furnace slag, we need to ensure how much potential there is for these heavy metal ions get leached and they get dispersed into the environment. So there is this wonderful work here which is being highlighted. So this work, if at all you are interested in understanding how we can measure the possibility of these heavy metal ions getting leached by our blast furnace slag, I encourage you to look into this book, or this paper rather. So they essentially talk about different ways that you can study your blast furnace slag, and you can come to an understanding that if the blast furnace slag that you are considering, maybe from your own or from the neighboring blast furnace operation, if this blast furnace waste that is getting generated by a blast furnace of your interest, does it have a potential of leaching or not? You can get that understanding of the test measures that needs to be undertaken. All those informations are available in this manuscript. It's just a shout out to them. So it's in this manuscript, you will see all those nitty-gritty description on what experiments to perform in order to understand if the slag that I'm operating with has the potential of leaching these heavy metal ions or letting out these heavy metal ions into the environment. Now, apart from these chemical composition and the potential of leaching these heavy metal ions, when we consider the waste that are getting generated out from metallurgical operations, we generally categorize them in a approximate way. We categorize them into acid forming, acid neutralizing, and neutral ones. So what we essentially here have in this case is, so we have something called as acid forming, we have something called as non-acid forming, and the other end of the spectrum we have acid neutralizing. So blast furnace slags are in general acid neutralizing agents. So acid forming is when exposed to environment they tend to form acid, and acid neutralizing is they tend to rather neutralize this particular operation of acid forming. So because of their chemical composition, because they have significant amount of calcium carbonate and calcium oxide, and through these reactions they are able to counteract the acid formation. So meaning, if you have a greater pH using this blast furnace alone, or blast furnace slag alone, you will be able to bring down the amount of pH in the system wherein you are using your blast furnace slag. Now, of course, there are sulfides, some portion or some amount of sulfides might be present in your blast furnace slag. So sulfide is rather a well-known acid forming agent, but fortunately for us, this amount of sulfide that is present is in the trace amount. So the acid neutralizing potential of the blast furnace slag is able to overcome the amount of sulfide that is present in the system. So therefore, the entire blast furnace slag is acid neutralizing in nature. So essentially what we have is, we have a blast furnace slag that has these three primary components: silica, calcium oxide and alumina, and it might have the potential of for releasing heavy metal ions under certain conditions. We have test methods to rather ascertain them, and generally our blast furnace slag is acid neutralizing in nature. So this essentially talk about the chemical nature of the blast furnace slag which we want to manage. So the entire series of these sessions are to manage the blast furnace slag. Now, apart from the chemical nature, we want to also understand the physical nature, the mechanical nature of the blast furnace slag if we want to manage them, put them. So if you want to efficiently manage them, we want to put them into good use. So if you want to do that, we also want to understand the mechanical nature of these blast furnace slag. So the mechanical nature of the blast furnace slag essentially depends on the way we cool them. So when during the blast furnace operation, when the iron is getting extracted, the way we receive the slag is in the molten state. So depending on how we cool this molten blast furnace slag, the arrangement of the molecules that constitute the slag varies. Correspondingly, the mechanical behavior of these blast furnace slag vary. So depending on how we cool them, we have different forms of blast furnace slag, and that is the reason why when we sell them specifically stating that the slag that we have is rather a granulated slag. So it means the slag is produced or it's cooled by spraying water on them. So we have different ways of cooling them. Depending on which way you adopt, you're going to have a different crystal structure, and that is going to give us different properties. And depending on the different mechanical properties, you essentially will have different application, different areas wherein these blast furnace slags can be employed. Now, to start with, when we have, or let's do one thing. Given that this is going to be a series of sessions, we will break it down into sessions of less than 20 minutes, and then we will try to make these contents that will essentially make these contents more palatable. So what we'll do is, for this session, we will wind up here, and in the next session, we will begin where we left off. Essentially, we will talk about when we have these chemical compositions and when we have these forms of blast furnace slag, where can we use them? What is the best way to manage them? So far we have understood the chemical nature, we have understood the mechanical feature or through its atomic arrangements of the blast furnace slag and from where it appears. In the next session, which will again we will start in a minute, we will talk about where the blast furnace slag, given its chemical composition and the mechanical properties, can be profitably rather employed and efficiently managed. Goodbye guys.